So in the last class, I sort of gave a lot of preliminary gyan about neutrino oscillations, and today we will start the formal discussion of neutrino oscillations, and we will cover the following topics. First, we will talk about oscillations in vacuum. In two-flavor mixing. Then this is of course obviously the algebra related to two-flavor mixing is simpler compared to algebra related to three-flavor mixing. So to get an appreciation of what oscillations are about without being overwhelmed by the algebraic details, we will consider this first, and then we will consider vacuum oscillations in three-flavor mixing. And when we go from two flavors to three flavors, not only is the algebra more complicated, but there is also new physics concepts come in. The situation actually is quite similar to what happens in the quark sector. When we have two flavors, there is no possibility of CP violation, but when we have three flavors, the possibility of CP violation arises. And then we will talk about then these two will be purely theoretical discussion, and then we will talk about how the relation between experiments and three-flavor oscillations three-flavor vacuum oscillations. Then we repeat this whole discussion now for matter effect. So oscillations in matter or again, we limit ourselves to two-flavor oscillations because we want to see the effect of matter on oscillations. So we want to concentrate on that aspect without getting lost in algebra. And moreover, for matter oscillations, this is a simple result you should remember from linear algebra. A 2x2 matrix you can diagonalize algebraically, but you can't do so for a 3x3 matrix. Or another way of saying it is, a quadratic equation you know how to solve. It's been known for 2000 years. but solving a cubic equation is much more difficult. So we'll have exact solutions in the case of two-flavor oscillations, but three-flavor oscillations with matter effect, we have only approximate solutions as far as algebraic expressions are concerned. If you are doing it numerically, then you can do it precisely to whatever accuracy you are able to design your code. Yeah.
There are solutions for cubic equations also.
Yes, but I mean, the solution to cubic equation looks much more complicated than solution to quadratic equation. So, given the training that we have received in algebra, we are able to visualize solutions to quadratic equations, but we are not able to visualize solutions to cubic equations. It requires more special training. So that's why I'm saying it's sort of okay. If you insist on writing a solution, I guess one can write down an algebraic solution in diagonalizing a 3x3 matrix. If I give you a matrix of 9 arbitrary elements, A, B, C, D, E, F, you can write the diagonal form of that matrix in terms of A, B, C, D, etc. But the algebraic expressions will look so complicated that what those expressions are telling you, it's difficult to follow. Whereas if I have a simple matrix, actually simple symmetric matrix A, B, B, C, I can diagonalize it and I can understand what those expressions are telling me. By the way, I usually tell this famous story about solving the cubic equation. Did I tell it someday? I didn't tell you this story. Actually, there is a book in the library by Simon Gindikin, Gindikin. There's a Russian magazine called Quant, which is addressed to sort of students of high school, college, students of mathematics in high school and college. And this Simon Gindikin had written various articles for that magazine, which turned out to be very popular. So those articles were collected and published in the form of a book, and later that book was translated into English. So I think the title of the book is called Articles from Quant or some such thing, but name of the author is Simon Gindikin, and in one of those articles he discusses this solution to the cubic equation, and actually there was a big controversy which it generated, and it's a very nice, interesting article, and you should read it. But let me sort of digress a little bit and talk about one important aspect of this solution to the cubic equation. When you solve quadratic equations, you have a square root of b square minus 4ac, and for some values of a, b and c, b square minus 4ac is positive, so one knew how to take the square root. But what if b square minus 4ac is negative? So people said square root of negative numbers don't exist. I mean, one shouldn't even think about square root of negative numbers. And that was the attitude people had until this episode that I talked about, where around 1500 people learned how to solve cubic equations. And during the course of solving cubic equations, they made a, you can say, curious discovery. I start with a equation, cubic equation, I know, which has 3 real roots. But then people have developed an algorithm to solve the cubic equation, and in the course of applying this algorithm, you would come across square root of negative numbers. So, I know roots exist, but in the intermediate steps, I have the square root of negative numbers. So if I say I shouldn't consider square root of negative numbers, then I cannot apply my algorithm to this problem. But, and this is where somebody made a leap of imagination, I define a quantity, which we now call I, to be square root of minus 1. So that I squared is minus 1. And I treat it like any algebraic quantity and do my manipulations. And if I do so, algorithm works and I get 3 real roots. So, it's a very important conceptual leap somebody made, that you need not be afraid. People were literally afraid of negative numbers, and square root of negative numbers are not even to be thought of. But this person says, no. Just as you can think of square root of 2. People were afraid of square root of 2 also until Pythagoras came and gave a geometrical interpretation of square root of 2. He said, don't be afraid of square root of minus 1. Just treat it as some abstract quantity which follows the usual rules of algebra. So that was the first time imaginary numbers and complex numbers were used in mathematics. Then I will not do the derivation, but I will conceptually discuss Two-Flavour Oscillations in matter, and finally the relation between the experiments and Two-Flavour Oscillations in matter. So we will sort of systematically develop. We start from the simplest possibility and keep adding one complication at a time. So our starting point is that there are definitely two neutrinos, two different neutrinos which have nothing whatsoever to do with each other. One, when it interacts, produces electrons, other when it interacts produces muons. So these are what we call interaction eigenstates. And as far as people knew, they are actually massless. And if they do have mass, that mass is quite small. And this is the argument made by the three Japanese physicists who said that mass eigenstates, these need not be mass eigenstates. Instead, mass eigenstates are orthogonal linear combinations of nu e and nu mu. I should have written nu1, nu2 is matrix times nu e, nu mu, but since what we see in the lab are nu e and nu mu, by convention we write it like this. Anyway, writing it the other way, I just have to take, this is an orthogonal matrix, so I just take the conjugate, transpose of it. And we are choosing this to be an orthogonal matrix because we want nu1 and nu2 to be, again, not have anything to do with each other. We want them to be linearly independent. Rather, not only linearly independent, we want them to be orthogonal states. And also, probability should be conserved that nu e has to go either into nu1 or nu2. It cannot disappear into thin air. So that constrains this matrix to be orthogonal. And this nu1 has mass m1 and this nu2 has mass m2, and rather I will write the two masses are not the same. What if the two masses are the same? Then any linear combination would also have the same mass. So it is just saying, okay, nu e has mass m, nu mu has mass m. Then the label mass is not distinguishing any state if both masses are the same. So we have to assume m2 is not equal to m1. And of course, theta is not equal to 0, because if theta equal to 0, this is an identity matrix, and so nu e has mass m1, nu mu has mass m2, nothing more to talk about. And now, this is the important point. What do I mean by a mass eigenstate? Well, typically in quantum mechanics, we have a Hamiltonian, and Hamiltonian has a set of energy eigenvalues, and under the influence of this Hamiltonian, these energy eigenstates will evolve. Also, corresponding to energy eigenvalue, there is an energy eigenstate, and under the influence of this Hamiltonian, which has the state some psi I, and under the influence of this H, psi I of t becomes e power minus ei t by h cross. That is the sort of foundation of quantum mechanics, if you wish. And we are considering quantum mechanics of neutrinos. Our neutrinos, we expect them to obey quantum mechanics, actually quantum field theory. So, let us consider the free particle Hamiltonian, which will be root of p square plus m square. So, if a particle has a definite mass m, then that particle also, and that particle when it acquires momentum p, will have energy given by p square plus m square. Let's also actually look at it from a more fundamental quantum field theoretic point of view. You have all learnt about, in your quantum mechanics, irreducible representations of angular momentum, and there is a corresponding concept in quantum field theory which goes under the name Wigner's theorem or irreducible representations of Poincare group. So Wigner proved a very famous theorem in 1939, where he asked, if I want to construct a relativistically invariant Lagrangian, what should be the primary building blocks? People have constructed various different Lagrangians, but we apply the same concept as in angular momentum. If I know the irreducible representations of angular momentum, just like I put Lego blocks together to build a stable structure, I can put these irreducible representations of angular momentum in an appropriate manner to construct a rotationally invariant Hamiltonian. Similarly, if I want to construct a relativistic a Lorentz invariant Lagrangian, I need to find the irreducible representations of the Lorentz group, actually of Poincare group, which is the larger group. So Wigner tried to classify these irreducible representations of Poincare group. And if you remember, the irreducible representations of Lorentz group, of rotation group, they are labeled by the number j. And of course, within each representation, the various states are labeled by m going from minus j plus 1 ... So, and j, if you remember, is the eigenvalue, or j into j plus 1 is the eigenvalue of the operator j square, and j square is jx square plus jy square plus jz square, which has the property that it commutes with jx, commutes with jy, commutes with jz. Such operators are called Casimir operators. So Casimir operator commutes with each of the generators. Jx, jy, jz are the generators of rotations, and this Casimir operator j square commutes with each of them. Similarly, we can define, this is actually a theorem from group theory. Somebody proved that one can label a representation of a group by the eigenvalues of its Casimir operators. So what are the Casimir operators for Poincare group? And Wigner found that the Casimir operators for Poincare group are this p square minus p square, that is 1, and also the j square of angular momentum. These are the Casimir operators for Poincare group. So eigenvalues of this and eigenvalues of this together will label the irreducible representations of Poincare group. And of course, eigenvalue of this is the mass. So mass eigenstate that way has a very fundamental importance in quantum field theory. If I am to define a particle, if I want my particles to be irreducible representations of Poincare group, then those particles should have definite mass and definite spin. So that is why the mass eigenstates, they are very important. And what the Maki, Nakagawa and Sakata said is that the mass eigenstates, as far as neutrinos are concerned, they need not be interaction eigenstates, but instead they are linear combinations. Now, let us assume that a beta decay has taken place and a nu E is produced, which I call my neutrino state at time t equal to 0. And okay, by looking at that matrix equation, this is cos theta nu1 at time t equal to 0 plus sin theta nu2 at time t equal to 0. So, how does this neutrino state look at a later time? This is cos theta nu1 of t plus sin theta nu2 of t. But I apply this rule and say that this is cos theta e power minus I e1 t nu1 at 0 plus sin theta e power minus I2 t nu2 at 0. But this, what I call nu1 at 0 is a sort of mass eigenstate without any time involved. It's just the definition of a state, which now I can invert. I can now invert this matrix equation and write in terms of nu1 and nu2, rather in terms of nu e and nu mu. So if I do that, I will get cos theta minus I e1 t times cos theta mu e, not plus, it will be minus sine theta e power minus I e to t sine theta nu e plus cos theta. And then of course next step is obvious. When I have some complicated looking equation like this, I gather all the terms corresponding to a given unit vector, I put them together. So I get the coefficient of nu e is cos square theta e power minus I e1t plus sine square theta e power minus I e2t times mu e plus minus sine theta cos theta e power minus I e1t plus sine theta cos theta e power minus I e2t times this, mind you, is so, I mean, this looks almost like magic, though anybody who has sort of done calculations of quantum mechanics shouldn't surprise you. But at t equal to 0, my neutrino state is pure nu e. But at a later time, I have some amplitude for it to be in the nu e state and some other amplitude for it to be in the nu mu state. So, what started out as electron neutrino is spontaneously turning into a muon neutrino. Not completely, but there is some probability for it to turn it into muon neutrino. And of course, as I mentioned before, if M1 equal to M2, E1 equal to E2, so this term drops out and nu e remains nu e. And similarly, if theta equal to 0, sin theta here is 0, this term drops out, only cos square theta is there, and again nu e remains nu e. So, for this nu mu, for the nu mu component to develop, I need theta not equal to 0 and M2 not equal to M1.
Yeah. E is under root of p square plus m2.
Yeah.
So what if momentum is different but
Yeah, we'll discuss that. Let me finish this part of the calculation and we will discuss that. Okay, actually, let's discuss it right now. Yeah. So, this point we discussed in the last class to some extent, that we want, if the particle is on mass shell, then it must have E square minus P square equal to M square. So if M2 is equal to M1, then see, neutrino is being produced in a reaction, and we insist that energy is conserved in the reaction and momentum is conserved in the reaction. So if I know the energy and momenta of all the other particles, I know the energy of the neutrino, I know the momentum of the neutrino. But then if M1 and M2 are different, how can I get E square minus P square equal to M1 square and E square minus P square equal to M2 square? This was the difficulty we had, and I discussed about how to overcome this difficulty using the concept of quantum mechanical uncertainty. But if I put M1 equal to M2, then there is a single mass, and in principle I have E square equal to P square. I have E square minus P square equal to M square. So I'll have E1 equal to E2, and this one will vanish. But later we will eventually make what we call equal momentum approximation, but that's an approximation, and the details of that I will discuss in a few minutes. Yeah.
E1 and E2 are the energies of neutrinos.
Of the mass eigenstate nu1 and the mass eigenstate nu2. Neutrino is produced with energy E. We are talking about a reaction producing a neutrino, and in our usual everyday language we say that it's produced with energy E and with momentum P. But the neutrino oscillation is an intrinsically quantum mechanical phenomenon, which means I must think of E not as a single number but as a range, E plus minus delta E. Similarly, I must think of the momentum as P plus minus delta P. And the only if delta E and delta P are large enough, then I can have E square minus P square will have a range, and both M1 squared and M2 squared will fall within that range. Only in that situation I will get these oscillations. For example, I have an electron and a muon, and in principle I can apply this formalism there. Say that electron and muon mix form mass eigenstates ... But mass of electron is half MeV, mass of muon is 100 MeV. So this construction that I just talked about will not apply there. So I either get electron or muon. I will not get admixture of the two.
So the amplitude would be very less before.
If you want to talk in that language, I wouldn't say amplitude will be very, very less. What will happen is, if I imagine a coherent superposition, that coherence is lost almost immediately. And if you want, you can estimate the time scale over which the coherence is lost, and you will find it will probably be some 10 power minus 23 seconds or some such thing. So I also mentioned, if M1 is not equal to M2, initially the two wave packets overlap completely, but since the two of them are moving with different speeds, they begin to separate. At the time of detection also, I need significant overlap. Only then this oscillation phenomenon can be observed. if the two packets completely separate, then the time dependence part gets lost. So, and what happens if you try to apply this formalism to electron and muon? What will happen is that the coherence is lost within 10 power minus 23 seconds. So I have either, actually that's not a correct statement. In the case of electron and muon, loss of coherence is not the issue. The issue is I have the quantum mechanical uncertainty associated with production of electron, or the quantum mechanical uncertainty associated with the production of muon. They are small enough that the range of E square minus P square, it either is around ME square or around MU square. It cannot span both. That is the reason. So that's why I have either electron or muon, never an overlap of the two.
Very small.
No, but I mean, okay, I have to then formulate my theory that if E square minus P square has a form which is sharp Gaussian around ME square, what is the probability of that Gaussian reaching up to MU square? So it is e power exponential minus MU square by ME square, which is exponential minus 40,000. Well, if you want to consider such numbers, fine. Okay, that is the amplitude with which you can find a muon when I have produced an electron.
In an experiment, let's say we have a two-body decay in which one is a neutrino. Let's say it's a muon type neutrino. So that will have a wave packet.
Yeah.
So that wave packet is a admixture of nu1 wave packet and nu2
wave packet, right?
So are the two wave packets same or similar? I mean, are the momentums of the two wave packets?
In principle, they need not be.
What determines it? Like, how do they?
No. But let me see. The two wave packets, in principle, can have different momenta also. But I'm not going to prove it. I'll refer, if you want, you can read it up in this textbook of Giunti and Kim, where they do a thorough discussion of the wave packet description of neutrino oscillations. The answer you get, whether you assume different wave packets of different momenta, or answer you get assuming wave packets of same momenta, you get the same answer in both. So to keep the algebra simple, we make the assumption that the two wave packets have the same momentum. We'll only assume that the energies are different. But that is equal momentum approximation to keep the algebra simple. I mean, if you want the full algebra to be worked out, I suggest you read the corresponding chapter in the book of Giunti and Kim. It's called Physics and Astrophysics of Neutrinos. So we have this, and we write this as AE of T mu E plus A mu of T mu. So AE of T, of course, is the overlap of nu E, or rather overlap of the neutrino state at time t with nu E, and similarly for a nu. And the probability that a neutrino which starts as nu E and is detected as nu E is mod AET square. So from the first term we get cos power 4 theta. From the second term we get sin power 4 theta, and then there is an interference term, and the interference term is twice complex conjugate of the first term times the second term. So it is 2 sin square theta cos square theta e power minus I e2 right. Clearly, cos power 4 theta plus sin power 4 theta plus 2 sin square theta cos square theta e power minus I e2 minus e1 times t. This cos power 4 theta plus sin power 4 theta I write as cos square theta plus sin square theta whole square minus something. So this is 1 minus 2 sin square theta cos square theta times 1 minus, oh sorry, I made a mistake. Probability, of course, has to be a real number, and I have put a complex number here, which obviously is a mistake. I should have been more careful. Yeah. So the interference term is complex conjugate of the first term times second term plus first term times complex conjugate of the second term. So it is twice real part of complex conjugate dot dot dot. So this should be real part of e power minus I e2 minus e1 times. I forgot to put that real part, which of course is cosine of e2 minus e1 times t. So this I will write as 1 minus 2 sin square theta cos square theta, and this term I will combine it with this to get 1 minus cos e2 minus e1 times t, and 1 minus cos theta is 2 sin square theta by 2. So, and that 2, when I bring it here, I have 4 sine square theta cos square theta, which is sine 2 theta whole square. So and I will not explicitly do this, it will be quite easy for you to do the other calculation. P mu e oscillating into mu at time t, it will be sine square 2 theta sine square of E2 minus E1 T by 2. And of course, there are only two possibilities. Nu e remains nu e or nu e oscillates into mu. So these two probabilities, if I add, I will get 1. This is of course a consequence of my transfer matrix being orthogonal. If my transfer matrix had not been orthogonal, then this probability conservation would not happen. It wouldn't have happened. And now E1 in general is P1 square plus M1 square, and any neutrino that we can detect has to be ultra relativistic, because in order to detect a neutrino, it has to interact and produce electron, and electrons have mass MeV or so, or in the case of mu1, 100 MeV. Whereas neutrino masses are electron volts, so they are ultra relativistic. So I take P out, so this is P1 plus M1 square by 2P1, and similarly P2 is P2 plus M2 square by 2P. And as I mentioned before, to keep the algebra simple, we make equal momentum approximation. That is, we take P2 equal to P. So we have P2 minus E1 is equal to M2 squared minus M1 squared by 2P, which we now approximate as M2 squared minus M1 squared by E, where E is the average energy of the neutrino. So the difference between E2 and E1, I have the leading difference I have extracted, and once I have extracted the leading difference, I will ignore the difference between the two here in the denominator. So E2 minus E1 by T, this is m2 square minus m1 square times L over 4E, where I have replaced the time of travel T by distance of travel L. L is the distance between the source and the detector. And I just mentioned that these particles are ultra relativistic. They have a gamma factor of at least a million. So beta is, what is the definition of beta? 1 over square root of 1 minus 1 over gamma square. So gamma is a million, means 1 over gamma is 10 to the minus 6. Square of that is 10 to the minus 12. So beta will differ from 1 by a number of the order of 10 to the minus 12. So we can safely take that these things are traveling with speed of light. So I replace the time of travel by distance of travel. And now this is appearing as argument of a sine function, so it should be dimensionless. So this quantity also is dimensionless, but usually we want to, so in natural units this is dimensionless, but we want to use regular units, so we have to restore dimensions. So by the way, this m2 square minus m1 square we call delta m square. That has dimensions, masses we consider in energy units. So that has dimension EV square. So this is delta m square I express in EV square, and L I express in meters, and 4 times E I express in MeV, or let me not say MeV, E also I will express it in EV. So numerator is this EV will cancel this EV, so net dimension is EV times length. And what combination of H cross and C has dimension energy times length? H cross C. This you should remember. As they say, if somebody wakes you up in the middle of the night, you should give this answer. H cross C is 197 MeV per me. So if I express delta m square in EV square, L in meters and E in EV, the net dimension is EV meters. So I will also convert this into EV meters. So this is 197 into 10 to the 6, and Fermi is 10 to the minus 15. EV meters. So I divide. By the way, this 197, well, let's keep it 197. So this argument is now delta m square in EV square, L in meters divided by 4 times E in EV, and this is 1.97 into 10 power 8 and 10 power minus 15. So that is 10 power minus 7. I have to divide by this. So 1.97 in the denominator times 10 power 7 in the numerator. And this E in EV is E in MEV times 10 power 6. I have energy, let's say 6 MeV, that is 6 million electron volts. 6 into 10 power 6 into electron volts, or 6 MeV. So, and so it means that I have this argument delta M square EV square L in meters by E in MeV. So this 10 power 6, 10 power 7 cancel, leaving behind a 10. I have 10 divided by 4 into 1.97, which this number turns out to be. So when we write oscillation probabilities, we always express delta M square in terms of EV square, L in terms of M meters, or E in terms of MeV, or sometimes L we express in terms of kilometers, and then we have to scale this also. Instead of MeV, we express this as GeV, and that argument we multiply by 1.27 to get the correct factor. So we have P mu E to mu E is equal to 1 minus sine squared to theta sine square 1.27 delta I square L over E. So whenever you see an expression like this, it is taken for granted that delta M square L and D are expressed in appropriate units, and we can define 4 probabilities: electron neutrino to be electron neutrino to go into muon neutrino to go into electron neutrino, and muon neutrino to remain muon neutrino. But because of probability conservation, we find that P mu E to mu E is equal to 1 minus P mu E to mu mu. This is also equal to P mu mu to mu mu. And we also find P mu E to mu mu is equal to P mu E to mu. But you will see that when we go to three-flavor oscillations, these relations are no longer true. What's the time? 12:36. 12:36. Okay. And now let's consider some approximations. Now, how do we actually observe the effect of these neutrino oscillations? So, simple thing, we take a neutrino source and we estimate or we make some measurement of how many neutrinos it is emitting, and then based on which we put a detector some distance away and we calculate how many neutrinos events we expect to see in the detector, and then we actually make a measurement of this detector far away, and if I observe less number of events compared to what is expected, I say, okay, it's likely that there is a neutrinos are oscillating. So basically a deficit of observed rate is considered a signature for neutrino oscillations. By the way, this whole business of ever since the solar neutrino experiment of Ray Davis, people have been talking about neutrino oscillations. So that's about more than 50 years. And in all this time, people have observed only these so-called deficit, that is survival probability less than 1. In very, very small number of cases, people actually observed these kinds of things, what we call oscillation probability. I start with one flavor and observe a different flavor. So we make this distinction. These probabilities we call survival probability. Initial flavor and final flavor are the same. And to some extent, those experiments are simpler to do. Whereas, these are called oscillation probabilities. I start with one flavor and look for a different flavor. So far, so if I am looking at 3-flavor oscillations, you can just do the simple counting. There are 3 survival probabilities and 6 oscillation probabilities possible. But so far, only one oscillation probability is actually measured, that is this one. There are a lot of practical difficulties in measuring other oscillation probabilities. So, we try to extract the best physics possible based on this oscillation probability. Anyway, that's a story for a later class. But the basic point I want to emphasize is as a practical matter, we make a distinction between survival probabilities and oscillation probabilities. And survival probabilities are easy to measure. Now, under what conditions can I measure the survival probability and establish that, okay, the survival probability is less than 1? Suppose theta is very, very small, then obviously it's very difficult to measure that the survival probability is less than 1. So, first condition is theta should be large enough how large is large enough? That of course depends on my experimental design and other considerations. But based on the expression, we immediately see that I should have some moderately large value of theta in order to measure this deficit. That is not enough. The second condition is that this delta m square by L, it should be large enough also. Again, because if theta is large but this is very small, then also I cannot measure the oscillation probabilities. And one of the reasons why people didn't take neutrino oscillations so seriously for a very long time is because nature chose the delta m square values to be very, very small. So in all the neutrino experiments with man-made sources that were done in the 60s, 70s and 80s, this quantity is too small. So there was no signal and people found the survival probability to be 1 in almost all cases.
Oscillation experiments were done in 70s.
Well, okay, not quite oscillation experiments were done in the 70s. The experiments that were done in 70s are neutrino deep inelastic scattering experiments. Because there was the electroweak theory which predicted that there is a neutral massive gauge boson. So to see the effect of this neutral massive gauge boson, you needed to, if you do an experiment with electrons or protons, the electromagnetic interaction is so much larger compared to this neutral weak interaction that it's very difficult to see. So one needed a particle which has this interaction but no electromagnetic interaction, and that particle is neutrino. So people built powerful accelerators with powerful neutrino beams. And as a sort of a side study, they looked at the possibility of oscillation. But later, people built dedicated experiments at lower energies with the idea of actually measuring neutrino cross sections more accurately. And there, again, the main physics goal is to measure the cross section, but as a secondary study, they would also look for evidence of oscillation. But only when the analysis of solar and atmospheric neutrino data indicated that delta m square. To explain the solar data, one needed delta m square 10 to the minus 4. To explain atmospheric data, one needed delta m square 10 to the minus 3. Only then people realized in all these experiments, the source detector distance is like 100, 200, I don't know, maybe few hundred meters. So one realized you need actually hundreds of kilometers. So, and that happened only in 2000 and later. And I mentioned that as far as the man-made sources are concerned, E is sort of fixed. In the case of reactors, E is like 3 to 10 MeV. It's not possible to have any other value of E. In the case of accelerators, things are under your control, and there you can actually design E from 0.5. But of course, it's more difficult to control things at lower energies, easier to control things easy to focus at higher energies. So, as I said, the solar and atmospheric neutrino experiments have given a hint as to what the values of delta m square are to be. And in the case of reactor experiments, range of E is fixed, which means that only thing under your control is L. And of course, there are all the additional constraints. You want some hill or something, or you want a mine so that the cosmic rays can be blocked, etc., etc. So you do an optimization study so as to get a value of L so that this is as close to 1 as possible, and you have good suppression of cosmic rays, etc., etc. Whereas in the case of accelerators, by designing my initial proton beam, I have actually a much better control. So we have accelerator experiments. There is T2K with L of 300 kilometers with energy of about 700 MeV. We had MINOS, and now there is NOVA with L of 800 kilometers and energy of about 2 GeV. And then this future experiment DUNE is being planned, where the L is going to be 1300 kilometers and the energy will also be larger. So that is one point we have to keep in mind. And one thing you should realize is we do not have a man-made neutrino source, or for that matter a natural source either, with single value of E. Every neutrino source has a range of E, and typically E max by E min is about a factor of 3. Here I wrote 0.5 to 20, but that is for all the accelerators together. For a given accelerator, the range is such that E max by E min is 3 or 4. So what that means is this number is not a single number, but it will vary over a range. So if if delta m squared by L, if the value of delta m square or the value of L is chosen to be rather large, then if this happens, then if I change E by a factor of 2, let's say for E max, this number is 10. For E min, then this number becomes 30. So as E varies, this number is varying between 10 to 30, which means that that sine squared term is going through many cycles and it will get averaged out. So then P nu E becomes 1 minus half sine squared. So the energy dependence of my oscillation probability is lost, and if the energy dependence is lost, I lose the sensitivity of my data to delta m square. It is sensitive only to theta. So if I want to measure both theta and delta m square, I have to choose my L carefully so that this quantity is of order 1. If it is much less than 1, then I will not see any signal at all. But if it is much greater than 1, I will see a signal. My survival probability will be less than 1, but it is sensitive only to theta. It is not sensitive to delta m square anymore.
We can also measure the energies of the neutrinos.
Doesn't matter. The question is, what is your bin size? So, let's for example, we have this experiment diagram which is looking for oscillations where delta m square is 10 power minus 3, 2 times 10 to minus 3. But let's suppose they are looking for oscillations with delta m square of 1 eV square, which means this number, instead of being 1, is 300. So even within a single small energy bin of about half MeV, this quantity will vary over a large number of cycles, so things will get averaged out. So this number is really crucial. It is dictating a lot of experimental constraints. It is dictating the value of L and the value, in some sense, your bin sizes and a lot of other details. And also it is dictating how sensitive you are to what kind of oscillations. And one final thing, I mentioned that there were a lot of experiments in the 70s, 80s which looked for oscillations but didn't find any. So they all had a constraint, or in the case of accelerator experiments, it is 15 mu. This is less than some number, let's say 0.1. So, which means sine square to theta except that one has to be a bit careful. They just measured one number, measured by expected, and they found that number to be close to 1. So they said, but measured by expected means this quantity is a weighted average of the event expectation rate. So I should put this is the average value, not directly dependent on energy weighted average value. Now, as I mentioned here, so this quantity is a function of two variables, theta and delta m square. So if I draw a if I consider a two-dimensional plane defined by these two variables, this equation defines a curve equal to 0.1, defines a curve. So one side of the curve is ruled out, other side of the curve is up. How does this curve look? For very large values of delta m square, the experiment doesn't have any sensitivity and this average value is half. So for large values of delta m square, there is no sensitivity to delta m square. So I have a vertical line. Now let's consider very small values of delta m square. Then this sign is approximated by the argument. And as I said, there is a E also, but that E is averaged out. 1 over E is averaged out. So I have sine squared 2 theta and delta m squared whole square. So the equation looks like x squared y squared is equal to constant. And if it's xy equal to constant is a hyperbola, x squared y squared equal to constant looks like a hyperbola. But if you actually plot it, it will look sort of like this. It actually looks almost like a straight line, but it looks like this. And in between, the oscillatory nature of the sine square actually matters. And if you look at the curve, it will look like that. So if you look at any of the papers which talk about neutrino oscillations with man-made sources, all the curves look like this. So this is the curve where equality holds. So this region is ruled out and this region is the allowed region. This is the experiments where you just measure the total rate, no spectrum. But if you measure the spectrum, of course, you can have more detailed information, but that we will discuss later. In all these experiments, first they are looking whether there's a deficit or not, and they didn't find any deficit. So they set an upper limit on the deficit of this form, and that upper limit on the deficit translates into limits on delta m squared and sine squared 2 theta of this form. Okay, I will stop now.